Welcome back to the Little Shop of Horrors. Look who's back. Hot and sexy hot plate, which means we're going to do some science today. Oh, I got to get my scale. Just wait. Here, you can read that while you're waiting. Alright. Now, if you look at the ingredients list on the side of your internet router, you'll find out that it's mostly made up of lies. 67%, somewhere around there. Oh, there is some riboflavin in there, but that hardly makes up for it. However, there is a haven of truth out there, and that is mostly found in scientific journals. Now, because I'm more than just a little bit of what the French call un perdant, I do admit to spending some time looking at online journals for interesting articles, and I did come across this one, which is actually pretty fascinating. The title of this article is Processing Bulk Natural Wood into a High-Performance Structural Material. Now, who wouldn't want to read that? Just grabs you hook, line, and sinker. So without getting into the weeds, the short and curlies of this are that they are taking wood, regular old wood, and turning it into a structural material by taking some stuff out of it and then crushing it down. So after chemical treatment and densification, you end up with this product that is 11.5 times stronger and 10 times as tough. And the thickness, remarkably, drops by 80%. Now, I'm not counting on getting those type of results, but if we get even close to that, I think we'll call it a success. Here's the theory behind what we're going to be doing here, which is densifying wood. Plant cells, unlike animal cells, which are just a fat bag, have a cell wall around them. You probably remember this from high school biology. And that cell wall consists of a few different types of biopolymer. One of them, you'll probably know, is cellulose. Long strands of basically glucose, sugar, that are kind of bound together in a different way to make them undigestible to humans. And it's what we call fiber. Those strands are embedded in this cell wall. But what really gives it its structure is what's in between all those cellulose fibers. And that is a couple of different biopolymers. One of them is hemicellulose and the other one is lignin. So these lignins fill in the spaces between the cellulose fibers and give it its rigidity. Lignin happens to also be very hydrophobic, which prevents water from rushing into the cell. That allows the cell to regulate water in and out. So what this chemical treatment is going to do is hydrolyze away some of the lignin and hemicellulose from the cell wall. And what that'll allow us to do is compress it down. But you don't want to hydrolyze all of the lignin away, because that will just end up being a mush. And that's dictated by how long you boil the wood in the hydrolyzing solution. Now, another thing to consider is there's xylem and phloem tubes that run up and down the wood, right? You remember these things? These are the ones that transport food and water throughout the plant. So if you think there's a hole here, say a xylem hole, then once you've digested away some of the lignin, you're able to compress that and just squish that right down. So I think that's where a lot of the decrease in thickness comes from when you compress it down. So let's get started and hydrolyze some lignin. I'll put the link for this article in the down below here, but you're gonna need some sort of person on the inside if you want to get the whole article, otherwise you're just gonna get the abstract. That's one reason to have kids and send them off to university. Now, because of the way science works, you will find the materials and method listed in the article, which means you can do this at home, provided you can get your hands on what you need. In this case, all we need is sodium hydroxide, and if you remember from some previous videos, that's this stuff, crystal drain opener. You have to make sure it's 100% lye, otherwise it will have impurities in it, but this is pure sodium hydroxide. The other thing you need is sodium sulfite. Now, I didn't have that, but I did manage to track some down on the purveyor of all things good and evil and got myself a pound of it. Tough getting through the airport security with this, though. Alright, so what these researchers did was boil the wood in a chemical bath of 2.5 molar sodium hydroxide and 0.4 molar sodium sulfite for 7 hours. And I've got a couple pieces of wood here, pine and an oak, and we're going to boil it in this baking tin here. I think I probably only need about 1 liter of solution for this. So that's what we'll make up. So to do this, we're going to need to calculate how much of each of these constituents we need. We want to make a 2.5 molar solution of NaOH and a 0.4 molar Na2SO3. So that's our goal here. So let's do this for 1 liter. 1 liter. And moles is actually, or molar rather, is actually moles per liter. So we have 2.5 moles per liter. And you can see liters are going to cancel out here. We're just going to be left with the number of moles. So that is 2.5, not surprisingly, moles of NaOH. And to calculate how many grams that is, we're going to use the molecular weight of sodium hydroxide, which is 40 grams per mole, times we need 2.5 moles. And you can see that moles is going to cancel. We're going to left with grams. That's 80 twice 100 grams of NaOH. Oops. All right. So that's one. Second one is sodium sulfite. So we're same kind of deal. 50 grams of Na2SO3. So those are our values there. Easy enough. Okay, this stuff is a little bit caustic, so mask, good idea. Gloves, excellent idea. Get your kitchen scale out. Power it and tare it and zero it and put it into kilograms. First off, 100 grams of drain cleaner. Okay, we'll tare it. Need 50 grams of this. Now you're going to dissolve that in 1 liter of water, somewhere around here on stir bar. We are going to fill this up to about, I'll say 800 mil. We'll get this spinning. The motor on this thing is a little anemic. It'll get up to speed though as she heats up. And then we're going to add our stuff to it and dissolve it as much as we can. Now you're going to notice your beaker is going to get a little bit warm just on its own. So we're just going to let that dissolve. Well, it's starting to clear up. We might as well take a few measurements while we're waiting for this stuff to dissolve. And, well, yeah, let's do this in millimeters. So our pine, starting out at 16.3 mil. And the oak, 19.3. Little warm, that's looking pretty good. So I think we'll top it up to a liter. And stop. Read the meniscus, everybody. I think there's going to be some evaporation going on here, so we'll just fill this up with our solution and we'll turn on the heat. So I'm just going to cover this with foil and let it go. I'll check it every once in a while to see how things are going. Holy fuck, look what happened here. I guess a smart person would have known that the tinfoil wasn't going to last. The solution, I guess, is just too caustic for it. I have to look up what goes on there. Well, if you're not making mistakes, you're not learning anything. I'll try covering it up with a piece of tile this time, see if it can burn through that. Now, I'm wondering if my pan is actually going to hold up here. So, I think I'm going to transfer it to this Pyrex dish and go from there. It'll be a good time to flip them as well. The crazy thing is, I did have a bit of a niggle in the back of my brain about using that aluminum foil, but I ignored it as usual. I'd make a fucking terrible Spider-Man. Okay, time is up. It's been 7 hours. And you can see if I solved my floating problem with a jar full of nuts. Worked fine. So it does create quite a stew. So there's the pine and the oak. I'm going to keep this for now. I don't know what I'm going to do with it, but it's a very weird substance, so we'll store it and think about that. It should be chock full of lignin and hemicellulose, so who knows when that might come in handy. Oh, look at that. It busted in half. Huh. Interesting. Now we need to boil the residuals out of it, so we're just going to put it in with fresh water. Doesn't really say how many times to do this, I don't think. Several times. Yes. That's very scientific. Several times. We'll do it several times. I assume it's 3. So we'll boil it up for, I don't know, half an hour. Change the water a few times maybe. I'm just trying to get the sodium hydroxide and sodium sulfite out of there so it doesn't continue to degrade the lignins. I'm surprised how much came out of that. Flush it and start again. Wow. Crazy. So that's rinse number 2. Do it again. So am I mistaken, or the oak doesn't float? Yeah, the oak doesn't float anymore. The pine is still alright. Okay, we're going to call this the last rinse. It's still leaching color. I think that just might be from the oak. I don't really know. But don't think this is an indication that things are still going on in there. The next step, according to the materials and methods, is to press the blocks at 100 degrees Celsius and 5 megapascals, which I figure is about 700 psi. Now, I don't have anything to measure pressure, but I do know that a bar clamp can provide up to 2000 psi of pressure, and one of those squeeze trigger ones only go up to 200, so I don't want to use that. I'm going to use the bar clamps. I decided I'd press them between these scraps of porcelain tile, but here's the thing. If you just press these together with this, they crack. So in order to mitigate that, we're going to make a sandwich. So I'm going to put them between, so block, ceramic, sample, ceramic, block, and then squeeze the crap out of that. So this is what we're looking at here. There's where our color's coming from. It's just out of the oak. And I'm trying to capture some of it because I think I might have an actual use for this stuff. It might show up in another video, you never know. Yeah, look at that. 20 mils of black gold. Anyway, they're ready for baking. We're going to put them in now. So it's sitting at a balmy 200 F, which is around 100 degrees Celsius, which is what we want. So I spent the day yesterday babysitting my pressure sandwiches, which really just involved cranking down on these clamps every half an hour or so, just to keep the pressure up. Now it's time to take a look at the results. I realized shortly after this that my wood biscuits were only half baked. Even after a good 10 hours in the oven, they seemed just slightly damp, so I thought, oh, I'll just put them back in the oven and dry them out real good and then measure them. Or so I thought. Right, I've had these in the oven for maybe 10 minutes, and there's still a lot of moisture in here because it's actually swelling up as it kind of steams itself from the inside, which means we could probably compress this down further. Shit! So I'm not sure what to do. I think maybe I'll just try and clamp this one. So that's what I'm gonna do, eh? I've got it clamped down, but it's very possible I've already screwed this up by letting the pressure off before it was completely, you know. But we'll put it in the oven and just keep this going. Alright, now it's been 2 days of wood squeezing time, and I better hope that that third time a charms thing is bullshit, eh? So here we are. We'll crack these open and have a little measure. So there's our pine. That's pretty fucking impressive. Look at that. This is the oak. Just a fraction of what it used to be. Fucking amazing. Holy shit, eh? Okay. I can just tell by feeling this stuff, it's hard as hell. Dense, dense and hard. The oak in particular, because you know it's already a heavy wood and now it's been shrunk down into something that's quite small, so it feels dense. Feels like it's got some gravity to it. Anyway, this is really interesting. Now, I don't think we hit the 80% mark, but damn, that's still pretty good. Let's measure them up and see what we've got. Alright, for our oak here, we'll just take a representative sample here. We're looking at about 8.1 maybe. Here we've got 7.75, 7, or 8 rather, 7.8, 7.5. I could just take some samples and average them, but I'm just going to do that in my brain. 7.2 there, hey? I think we'd be safe to say about 7.5. Be all right, maybe 7.6. So let's write that down. Originally we had 19.3 and now we're down 7.6 millimeters. Now what about the pine? So let's have a little peek around here. 6 maybe. 6.7, 7, 7, 7. It looks like it's pretty close to 7. Let's call it 7. So now we need to figure out the percent decrease here. So to do that, we'll subtract the 2, find out what the change in width is. 16.3 minus 7. So we have 9.3 decrease in size, 9.3 millimeters. And we'll divide that by the original 16.3 to give us 57%. And for the oak, so not 80, 60, not 80, close. Close, close, close. Not really. Anyway, it's still pretty impressive any way you look at it. It's 19.3 minus 7.6 divided by 19.3. So that was 11 millimeters. Decrease in size 60%. Not too fucking bad, I think. I think that's okay for your first try at this, and with some very sketchy equipment. And you know, we followed the procedure as much as we could. Now, part of the reason this may not have worked as efficiently is, one, maybe because I took it out too soon and kind of screwed up the compression thing. That could be possible. So that would be one thing to change. You have to press her down for a good 24 hours at, you know, 212 Fahrenheit or 100 C, and just keep it at that until it's fully dry. Maybe we needed to boil it longer for whatever reason. They said 7 hours, but I know they did vary those parameters, so, you know, we could fool around with that to try and get a better result. I think that probably would allow higher compression. Third thing is, this is highly inaccurate. I have actually no idea what kind of pressure is being produced by this, and I don't know whether that pressure is constant. I mean, when I just tweak this down, if you looked at the wood, it's you know, crushing into this wood as well. So I may be cranking it down and not actually increasing any pressure on the inside. Well, there's got to be some, I suppose, but yeah, not very accurate and not very constant either. I'm sure they had a machine that actually maintained the pressure at 5 megapascals. So that's another thing to change. Anyway, third thought. This could be done under pressure. The chemical treatment could be done in a pressure cooker, for example. And that might speed up the process. And it also might drive more of the material, you know, have a more even, what would you say, dispersion of the material, of the chemical into the wood. That's something to think about anyways, because you may be missing areas even though you're boiling for that long. In any case, it would likely speed up the time that it takes to do this. Just some thoughts. I'm pretty damn happy with this. I'm actually quite impressed with the decrease in size. And yeah, fun experiment. Very fun experiment. And hard as hell, this stuff. This stuff is very, very hard. Sanding it, for example, when you sand it, what comes off is ultra fine, and there's it's very difficult to get anything to come off of it. It's not like regular wood anymore. Same with the pine, same deal. Very hard. Maybe not as hard as the oak, but still very, very hard. So, very impressive stuff. Anyway, I hope you really found that interesting. I sure enjoyed doing this. This was a cool experiment. Thanks for watching. Cheers. Now I just got to make enough of this stuff to side my house.